Okay, following along in the textbook, we're now to section 2.7, phase diagrams. And as I start off there, would you agree that the problem that we just finished, excuse me, in 2.6 took quite a bit of time, right? Quite involved. And solving differential equations, even ones that can be solved, sometimes is quite laborious. So I'm going to show you in this section a much simpler way to get at least a lot of the crucial information that you want from a solution to a differential equation. We don't get the actual solution like we did. Once you have the actual solution, you have everything you need. You can say what the temperature is going to be or what the population is going to be at any point in time. You know exactly what it is. This method doesn't give you all that, but it does give you the general sense of the solution. It gives you the general shape of the solution and the long-term behavior, which is often what you need to know. So in order to illustrate it, let's go back to Newton's law of cooling. Remember Newton's law of cooling? We said if the temperature in the room is 70 degrees, and if you take something out of the oven, then the rate of change of the temperature, where y is the temperature of the object, the rate of change of the temperature is going to be proportional to the difference in temperature between the object and the room, right? So in particular, if it starts off at 350 degrees, you've taken it out of the oven, and the room temperature is 70, then the temperature of the object is going to go down, which means that K is going to be a negative number because this is decreasing. So back in section 1.1, we actually found a value for K, and it was a logarithm of some number less than 1, so it was negative. Let's just put in a negative number here, which is just an easier one. Let's just make it negative 1/2 as an example. So negative 1/2. So there would be an example of Newton's law of cooling for something that you take out of the oven. So given that, remember we know how to solve that thing. It's a separable differential equation. You can divide both sides by y minus 70. You can multiply by dt. You can integrate both sides and get the answer easily enough. But instead of doing it that way, which we've already done, let's do it another way instead. And so the way we do it is we graph this equation. And by graphing this equation, what I mean is let me do it over here. We make this axis y and this axis dy dt. Okay? So here's your dy dt, here's your y. So don't get confused by this. Let's make things a little something simple, something more what you're used to. Let's just write y is equal to negative 1/2 x minus 70. Hopefully, I mean, that looks a little more familiar to you. Now your variables are x and y, and let's think how you would graph that. This graph is going to look exactly the same. All we've done is rename the axes, but let's go ahead and do it this way, just because it might be a little bit easier. What are the intercepts going to be? Notice that when x is 0, y is going to be negative 1/2 times negative 70, which is a positive 35. Agreed? It's going to be a positive 35. So there's your y intercept. And your x-intercept, if you want to know when will y be 0, okay, this is your x-axis. This is your y-axis right there. If you want to know when will y be 0, when will it be 0? This will be 0 when x is 70. So here you are at 70 right there. So there's the two intercepts, and once you have that, notice it's a straight line with slope of negative 1/2, which makes sense, and it looks like that. Okay? So this is going to be exactly the same thing. It's just all I've done is rename the axes. So let's make this 70 right there, and make this 35 right there, and so it looks kind of like this. Okay, so there's the graph of y dy dt versus y. Okay, so there it is. Now, question is, how will that graph allow us to get solutions, to at least draw solutions to this differential equation? And here's how we do it. It's really a clever technique. So now we actually want the solution. So the solution is going to be y versus time, right? It's your y, by the way, recall, as I already said it, but let me just say it again. Y of t is the temperature at time t. Okay? So, how do we find the solutions? Here's what we do. We start with a value. And again, I'm lacking board space here, so I'm going to have to make these graphs kind of overlap just a little bit. We start with a value. Let's start with a value of y, which is, say, greater than 70. Say we take this thing out of the oven, and it looks like if this is 70, maybe this is 100 degrees right there. Okay, so we take it out of an oven, which is 100 degrees. Let me go ahead and put 70 right here. There's 70. And we pull something out of the oven, which is 100 degrees. Okay, so at time equal to 0, this object is going to be 100 degrees. So there's 100 right there on this graph. Okay, so again, the hardest part of this is realizing that on this axis system, your y is on the vertical axis. On this axis system, your y is on the horizontal axis. Okay, it takes a little getting used to, but once you get the idea, it's really neat. Okay, so here's what you do. You think of putting your finger right here on this y. Okay, there's your y right there. You put your finger right there, and then you ask the question. You think of y as being this like an ant that's moving along this y-axis, and you ask, which direction and how fast is this ant going to move? Okay, this is y, and the value of the graph gives you the rate at which y is going to change. Do you agree? The value of the graph, this vertical distance here, that's your dy dt here, that's going to tell you how y is changing. So right here at 100, I look and I say, oh, what's dy dt? dy dt is a negative number. Since dy dt is negative, that means that y is decreasing. Agreed? If the derivative is negative, that means that the function is decreasing. So this thing here has to start moving in a decreasing way. It's got to start moving like this. As it moves, it continues looking straight down. In this case, it's looking down rather than up. It's looking down and saying, oh, dy dt is still negative, which means I have to keep decreasing. But notice, here I'm decreasing faster because this is a larger negative number. Here, this is a smaller negative number. And so I'm not moving as fast anymore. As I go, I keep looking and I keep noticing that I have to keep decreasing because dy dt is negative, so I have to keep decreasing. And I keep going until finally, I don't know whether I'll even ever quite get to 70. Because I get closer and closer to 70, I'm going to keep slowing down more and more. So that's the kind of graph we want to put here. We want a graph which starts decreasing rather fast, but as you get closer and closer to 70, it keeps decreasing, but at a slower and slower rate. So it looks something like that. And that's exactly the graph that we got when we solved this differential equation, and we ended up with an exponential decreasing function that looked like that. Okay, so there's how it works. Let's do another example. Suppose we take something out of the oven which is, I don't care, which is say 20 degrees. There's 20 right there. So here's 20. So I guess it wouldn't be out of the oven, it's maybe out of the refrigerator or out of the freezer. Okay, so you take it out of the freezer, it's 20 degrees, and now what does this graph say? Well, here's your y is the temperature, and I look to see how does y have to change, and now instead of looking down, I go straight up, and I say, oh, dy dt is now a positive number. Since the derivative is positive, that means that y has to increase. So I have to start moving in this direction. As I move, look, I have to continue to increase because dy dt stays positive. So I'm moving. I'm not moving as fast as then. I'm moving slower. Now I'm going to keep moving. I'm going to keep increasing, slower and slower and slower. Keep increasing, and finally get closer and closer to 70. So this graph would look something like that. Okay? It's going to be increasing the fastest right here, and then it's going to be slowing down. The slope is going to be a smaller and smaller number as you get closer and closer to 70. I guess there's one other example. What happens if something is already in the room? Or you take something out of the oven, but the oven is not on and it's 70 degrees. Then what happens to the object? Well, notice that now the derivative is 0, which means that the temperature doesn't change. So if you start at 70, you're just going to stay at 70. So it's going to look just like that. Okay? So that's the way it works. Okay? So there's an example. Now notice what you don't have. If I wanted to know exactly what's going to be the temperature at time equal to 5, say, this graph, there's nothing there that tells me exactly what this value is going to be at time equal to 5, okay? I know it's going to be less than 100, I know it's going to be greater than 70, but I don't know exactly what the value is. So if you want the exact value, you have to go ahead and actually count and find the solution to this. But quite often you don't need that. Quite often you're just interested in, is it cooling down? Is it warming up? What's the long-term behavior? You notice that the long-term behavior for both of these is that they get closer and closer to 70. That's often all you need. Okay? So that's that one. Let's do another one. Let's go back to the population one now. And we called it the population now. And so now y of t is the population at time t. And if we have a carrying capacity, then dy dt is equal to, what did we say it was? It was ky times, we have some sort of carrying capacity. Let's choose the same as in the book. The book I made the carrying capacity 100. So we'll make it 100. So it's going to be 100 minus y. Okay, and again, just to be specific, I'll choose the same thing that's in the book. We'll choose k to be some nice number. What did I choose here? I should have had this down. Let's see. Do I have it down? Let me see here. I don't know. Let's just choose it to be 1, just to be easy. Okay, so k is just equal to 1. Okay. Okay, so first of all, what does this graph look like? Okay, so over here again, we could graph it easily enough. Let's go ahead and do it, in fact. Right there. And notice it's going to be a parabola. It's a parabola with intercepts at 0 and 100. And if you were to multiply that out, it's going to be a negative y squared. Negative y squared means that it's going to be a parabola that's opening downward. So it's going to look something like this. It's hard to get that. Let me just move the 100. It's easier to do right there. Okay. So again, if you didn't know how to graph that, you could go over here and you could say, okay, f of x is equal to x times 100 minus x. And if you multiply that through, you're going to get negative x squared plus 100x. Agreed? And you've had calculus 1 now, so you know how to find where the vertex is. The vertex is going to be where the slope is 0. So you take the derivative, and the derivative is going to be negative 2x plus 100. And you want to know where will that slope be 0, so you set it equal to 0. And you solve it, you're going to get 100 is equal to 2x. X is equal to 50. So it happens right there at 50 is where the maximum occurs. And if you stick 50 into this thing, what are you going to get? F of 50 is going to be equal to 50 times 100 minus 50 is 50, which is 2,500. And I notice if you look in the book, it looks like it only goes up to 50. So it looks like let's see, 2,500 divided by what gives you 50? So x is equal to 2,500 divided by 50, and so those go 5 into 25, 250 divided by 5 gives you 5, 25, 50. So it looks like I had a fraction of 1/50th out there. So if you have a fraction of 1/50th out there, that'll raise this thing up. The vertex will still happen at 50, but now this will happen at the high point will be 50 as well. Okay, so you got that. Okay, so there's the function that I have actually in the book. It goes up to 50, and the vertex occurs at 50, and so it looks like that. Okay, so there it is, and so now that we have that, how can we find the solutions? What do the solutions look like? Okay, so what do? So let's do the same sort of thing we did before. Okay, here's your t, and here's your y right there. And since the carrying capacity is 100, let's go ahead and put 100 right there. That's kind of an important point. Let's see once what happens. Okay, so let's see once what happens. So first of all, what happens if you start with a population which is greater than 100? Remember what happens? If you have a carrying capacity of 100 and you start with a population greater than 100, then it's going to die down to that carrying capacity. And so sure enough, look at this. Here's the graph of the differential equation. Let me again make sure you understand this. This is y, and this is dy dt right there. Okay? And so what do? I start with a value of population which is greater than 100, and I look and I say, aha, the derivative is negative, which means y has to decrease. And the derivative continues to be negative, which means y has to keep decreasing, and I'm going to keep decreasing until I get to this. It's called a fixed point. Once it's there, it stays there. So if I start at something, say this is 130. If I start at 130, see, here's my y value. There's my y value. Start at 130. What's it going to do? It's going to decrease quickly at first, and then the rate of decrease is going to slow down. It's going to look something like that. Okay? What happens if I start, let's start at 50. Let's start at 50 right there. What happens if I start at 50? What happens to the population? Well, notice that the carrying capacity is 100. So I'm starting by moving to the right at a big speed, because this is a fairly large number there, right? It's a large positive value, so that means I'm going to be moving to the right. And as I move to the right, as y increases, I'm going to continue increasing, but it's going to increase at a slower and slower rate. So what do I want my slope to do here? I want it to start off at a large slope, because I'm moving quickly to the right. But then as I move on, now the slope has got to decrease. So it's got to look something like that. Okay, that's what happens if I start at 50. Make sure that everything is still on here. Okay, good. Everything's working. Okay, now, what happens if I start at, say, 5 instead? I start way down here. What happens if I start at 5? This is a great opportunity for you to turn off the video and see if you can do it on your own, okay? I'm going to do it as soon as in just a minute. So turn off the video and see if you can figure it out on your own. If you can, it shows you really understand what's going on here. If you can't, you still have stuff to learn, which is fine, but see if you can do it, okay? Okay, I'm going to assume you've tried it. Now, here we go. So we start at 5, what's happening? First of all, notice that dy dt is positive. Since it's positive, that means I'm moving to the right. Agreed? My y is getting bigger and bigger, and so over here it's got to get bigger and bigger. But notice what happens. As I move to the right, the rate of increase keeps getting larger and larger, right? Here I'm increasing, but rather slowly. Here dy dt is bigger. The height of it is bigger. Here the height is even bigger yet, which means over here the slope has got to be bigger. When I get to 50, that's where the slope has got to be the greatest, and then the slope starts decreasing as I continue on from 50. So starting at 5, my rate of increase is going to be increasing faster and faster. See that? That slope kept getting bigger and bigger until I get to 50. And once I get to 50, now it's still increasing. See that? It's still above the x-axis, still above the y-axis here. So it still increases, but it's increasing at a slower rate. So it looks something like that. Okay? So that's the idea. So notice if we started right at 100, that's called a fixed point. It doesn't change. If you start right at your carrying capacity, it just stays there. It doesn't change at all. And this tells us that. Notice that if we start at 0, it doesn't change. Does that make sense? Sure, if you have 0 population, it's not gonna increase at all. So that part makes sense. So again, this is very nice. Look how much easier this was than all that stuff that we did in the last lesson, where we had to go through all that material. And again, notice that if I want to know if you start with population of 5, when will you be at a population of 70? This graph doesn't tell me exactly the value of t where it's going to be 70. This is just an approximation. Maybe it looks more like this, you know, maybe it looks somewhat different. Okay, that's fine. I don't know exactly what it is, but I know roughly where it's going to be. And again, I know the long-term behavior. I know that you're going to be increasing for a while, and then it's going to be decreasing. I should say the rate of increase is going to be increasing, and then the rate of increase is going to be decreasing. The population keeps increasing all the way. It keeps increasing to 100, but the rate first increases and then decreases. There's an inflection point right there. There's a place where the concavity changes. So again, going back to COVID, we're in the middle of COVID right now. In COVID, the news keeps talking about inflection points. And I don't know whether the newscasters know exactly what they're talking about when they say it, but this is what the medicine is talking about when they say an inflection point. They're interested not only in are the cases of COVID increasing, But notice how much more promising this part of the graph is than this. Here they're not only increasing, but the rate of increase is increasing, right? It's getting greater. It's the rate of increase keeps increasing. Here, yes, it's increasing, but the rate of increase is slowing down, right? There's good news on the horizon. Eventually, it's gonna stabilize. Okay, so you're often interested in the inflection point, and that's the place where the concavity changes. And again, you can get all that just from these phase diagrams. Okay, you can see where the inflection point is just from the phase diagram. So there's that one, and I think from there on, I give you examples to do. Let's just get started on the first one. The first one I just say, suppose you have this differential equation. dy dt is equal to sine of t, or sine of y rather. Okay, dy dt, or I could say y prime, is equal to sine of y. Okay, well, hopefully you know what sine of y looks like. That graph just looks like this. Here you are at pi. Here you are at 2 pi. This goes up to 1, so on. Okay, so here's the graph of y and dy dt. Okay, this would be a very difficult, almost essentially impossible differential equation to solve. Even though it's separable, you're not going to get any nice solution there at all. So really kind of give up on the idea of getting a real solution to that, anything that's useful at all. So really the only choice you have here is these phase diagrams. Okay, so here you have t, here you have a y, and again, let's put in these fixed points. Let's put in points where if you're there, you're not going to move. Notice if you're at pi or at 2 pi, let's just take the positive part here. We could take negative pi as well, I guess. As long as you see that. Those are places where if you start there, you're not going to move. Just going to stay right there because the derivative is 0 there. If the derivative is 0, that means there's no change in y. If the derivative is 0, that means y isn't changing, so you're staying right there. So if you start at pi, you're going to stay at pi. If you start at 2 pi, you're going to stay at 2 pi. If you start at negative pi, you're going to stay there. On the other hand, if you start if you start at 0, notice if you start at 0, you're going to stay right there. Okay? So those are all fixed points. On the other hand, what happens if we start at this value? Let's see. Let's do one a little different than the ones I've done before. Let's start with this one right here, for example. So there's a value between pi and 2 pi. So it's starting right about there. What does the graph say to do? It says that the derivative is negative, and since the derivative is negative, that means I got to be decreasing. So I'm going to be decreasing. I first decrease rather quickly, but then I'm going to slow down as I get here. So my slope has to start with a pretty steep slope, and then it slows down. So it's going to look something like that. What if I start right here? Just a little bit under 2 pi. What's that going to look like? Well, notice that I'm decreasing because the derivative is negative, so I'm decreasing. And as I move, I'm going to be decreasing, so I'm going to be moving to the left. As I decrease, notice that the graph tells me that I got to start decreasing at a faster rate. So I start slow, I decrease at a faster rate until I get right here. Now I keep decreasing, but now it's going to be a slower rate. So again, it's kind of like an ant that's just walking along here. And as it walks, it just looks down to see how fast it should be walking. Here it's walking to the left, it's going faster and faster, and now it's slowing down. So the same thing here. It's going to start decreasing slowly, but then go faster and faster, and then start slowing down again. So again, there's an inflection point right about there at the midpoint, at 3 pi over 2. Okay, so it starts slow, decreases, and like that. Okay, so that gets you started. I can't remember what I asked you to do in the book, but basically I want you to draw these graphs for other ones as well. Start with some in here, maybe start a couple even in there. See once what you get. Okay, so there's phase diagrams. We're going to be using this from now on in the rest of this chapter because it's going to be really useful in finding solutions. Okay, very good.